Let's get started. We're going to start with the Hyatt Regency collapse. So this is 2 walkways. I think they're going to talk about it here in a little bit, so I won't talk about it too much. But it's a super tragic accident. A lot of folks died. A lot of folks were hurt.
Casualties were sent to nearly every available hospital in the area, while the dead were moved to a makeshift morgue in the hotel's exhibition area. The high number of casualties meant that almost everyone in the local area knew at least one victim. The psychic impact of the collapse was huge. An investigation was launched to find the cause, and its focus quickly narrowed to the construction of the walkways. Analysis of the wreckage showed that a change had been made from the original plans. The walkways for floors 2 and 4 were directly above one another. In the original plans, they depended from the same long hanger rods. But in actual fact, these long rods had been switched out in each case with 2 shorter rods. This seemingly innocuous switch had been made based on a proposal from the manufacturer of the steel rods. Long rods would have to be threaded along their full length and would thus be easily damaged during installation. Replacing each long rod with 2 shorter rods would make things much easier to manage, they said. And so 2 rods were installed in each case. It was never taken into account that this would change the forces which acted upon the walkways. In this new configuration, the beams of the 4th floor walkway, where the hanger rods were attached, now had to bear twice the load they had originally been intended to hold. This, combined with the number of guests crowded on the walkway during the tea dance on the 17th of July, 1981, was what had precipitated the collapse. Analysis of the wreckage revealed that the nuts holding the walkway in place had pulled all the way through the box beams against which they had been secured. While this was the main factor in the collapse, it wasn't the only issue highlighted by the investigation. Numerous other safety violations and breaches of protocol were discovered. During the hotel's rapid construction, preliminary sketches had been used as though they were final signed-off drawings, and changes to the design had sometimes been confirmed by a quick phone call, rather than by the submission of revised plans. The issue which caused the collapse of the walkways at the Hyatt Regency Kansas City Hotel was, according to the original designer, so obvious that a first-year engineering student could have spotted it.
Wow.
Tina Kotek called for a homeless state of emergency only 3 years ago.
It's annoying. So I have to mute her because I can't give her extra time, over other politicians. So the reason I like this failure to show in class, I don't like this failure, is because there's a solution to it. You can go online and find these kind of failures all over the world. It's scary, but you can't always get like the analysis afterwards, the understanding of what happened. So it's kind of nice to have that.
Unnoticed, with the various companies and contractors involved in the construction of the hotel, all assuming that someone else had done the work of verifying designs and running calculations. The disaster and the hundreds of deaths which resulted from it had been caused, in short, by poor communication and a laissez-faire attitude during a rushed construction project. The engineering firm, Jack D. Gillam and Associates, had been responsible for the original design and had approved the final drawings. In the aftermath of the disaster, they were stripped of their license to operate in 3 states, as well as their membership of the American Society of Civil Engineers. No criminal charges were pursued against the firm, but owner Jack D. Gillam, who had been an engineer of note on the project, was haunted by the disaster for the rest of his life. He spent his remaining years lecturing and speaking about his involvement in the hope that the story would scare young engineers out of making the same mistakes that he and his company did. More than 300 civil suits were brought against those involved in construction and management of the hotel. These lawsuits yielded billions of dollars in compensation, a large portion of which was set aside for charitable causes to help the Kansas City community heal and move forward in the wake of the disaster. Even when agreeing to pay out compensation, everyone connected with the case denied all legal responsibility. Numerous changes were made in the fields of civil engineering and construction in the wake of the disaster. The collapse was international news. In countries around the world, the curriculum for engineering students was completely overhauled, with a new emphasis on responsibility and safety. Standards were raised and trade manuals revised. The Wk collapse remains, to this day, a sobering case study for budding engineers.
All right, let's just look at this again. So the mistake the civil engineers made was not looking at the changes that were made. They just approved them via phone call. It all sounded good. So this rod is designed to carry both floors. So the rod here is designed to carry this floor on that nut and another floor on another nut. So the rods are fine. So everyone thought, oh, the rods failed. The rods did not fail. The rods were designed to carry two floors. So they had the capability, and we're going to actually talk about bending stress and tensile stress today because I want to arm you with some ability to do some calculations on your project, right? And you haven't had statics yet, and you haven't had strength materials, so you don't know those concepts. But I can give them to you in pretty basic form, right? But everything that we do is wrapped around what we call equilibrium. So this building is in equilibrium, thank goodness. Otherwise, it would be like falling on us, right? So that means all the loads on the building weight, everything equates to zero. Nothing's moving, right? The ground is pushing back at the same weight that the building's pushing down. So the building's not going into the ground. We get a big void underneath the building, a sinkhole or something, and the building falls into the sinkhole, right? The sum of the forces, it's not in equilibrium. So pretty much everything we do structurally, when we design, things need to be in equilibrium, right? So P1, they're talking about the load of floor 1, and then P2 would be the load of floor 2. When you change it to this rod is now carrying floor 2, the one down there. This rod is now carrying floor 1 and floor 2 like it was designed to do. It can do that. But now this nut, it is holding both floor 1 and floor 2. So this beam and that connection, which is the goofiest damn connection I have ever seen. You would never, I mean, I can't imagine having a structural piece go right through the seam of two beams that are pulled together. Like, that was a horrible design. That was pathetic. Anyway, that nut now is loaded twice. So one of two things are going to happen. Who knows if that nut was designed for that second load? So the threads literally could have just ripped off of that bolt, but that's not what happened. It actually sucked up and through that beam. But that connection right here was never meant for P2. It was only meant for P1. So pretty simple calculation. If you know what that box beam is made out of, probably out of steel, mild steel. Mild steel has properties, right? It can only do so much. It can only hold so much pressure. And if you exceed that pressure, then that material can't resist it. And that's when we get a failure. Okay? So it was a change. It was a change that was like approved over the phone without much thought. And that's where it went bad. So when you make changes, just try to verify that those changes are going to be as good as the original. Questions? Somebody knew. The guess was somebody knew about this change and probably knew that maybe that wasn't a great idea. Maybe not. Maybe it just got done so fast that no thought was put in.
Yeah, I was like, how long before the actual walkway collapsed?
Oh, it was in use for a couple years. Yeah, so the problem was it got loaded to full capacity, right? So most of the time walkways are not loaded to full capacity. So if you have a floor, not this floor because it's on the ground, like the floor above us, that design load to the floor above us, if there's movable furniture, this is all movable, right? So if you have a room with movable furniture, that's a different design load than if you have a room full of equipment and other things that can't move. Like maybe above us might be the science lab. No, that's probably not right. Science lab's over here somewhere though, right? Has a lot of fixed equipment. So that floor design load is different. If there's movable furniture, then you do the floor design load as if you have one person standing in every square foot. And you take the average person. So I don't know what they use for that number these days, but probably like 200 pounds or something for the average person. Who knows? In this country, right? Yeah. Anyway, that's how you come up with that design load, as if it's going to be stacked with people. It's like when you cross the Fremont Bridge in Portland, that's the big bridge, the double decker. Everyone's seen that one, been across it? Has anyone been stuck on it? I've been stuck on it. If you've ever been stuck on either level, like in a traffic jam, and the other level's going, man, you just sit there and bounce because the whole thing is like deflecting big time. But the design load on that bridge is the heaviest loaded vehicle that could drive that bridge, which is like a semi truck, fully loaded. And then those stacked up. Like that's the traffic jam of semi trucks fully loaded. Okay, so that's how we come up with these kind of loading conditions. Well, a floor is that way too. Every square foot, a person, which we don't usually get that. Like who wants to stand, shoulder to shoulder? Well, it was a party and a dance, and they got on the walkways shoulder to shoulder, loaded it to full capacity, and then played music. And then everybody jumps up and down at once, which like doubles the load, easy. And that's when it went. So let me tell you, if you're in a building and people start dancing and jumping around, it's like time to move to the edges. Get your phone out for the video, right? Anyway, yeah, that's how it happened. Got loaded to capacity. Questions? Yeah, be careful. Be careful on your design changes. Let's do this one next. All right. We're going to go over just probably each week. We'll hit some topics. Some will be repetitive, some won't be, but we're going to talk about some engineering disciplines. I'll try to field as many questions as you have about these as we go through them. We're going to go through them pretty quick, right? And then we'll take longer with the disciplines as we move through the class and trying to give you a feel for like what you could be doing. So I think that's important. Like things that are important that students don't typically think about is like how much desk time will I have compared to how much out in the shop time or outside time. Like if you're a person that wants to be outside a little bit now and then, mechanical engineering is probably not your path. Like we are typically in the office or in the facility, but actually outside sometimes, but not very often. Like not on a weekly basis are you going to spend 6 hours outside. Not going to happen. You might go out 1 or 2 hours a week as a mechanical. Yeah.
What about electrical?
Electrical is the same way, unless you're working with power transmission, right? So like if you're an electrical engineer and you go to work for PGE, then you're probably going to be moving around to their different power distribution areas and potentially getting outside at that facility, right? But if you're a double E that goes to work for Microchip, you're not only inside, but you're in one of them funny bunny suits too, right? So that is a little bit dependent, but mostly inside. Yeah. Yeah. Biomedical is going to be pretty much inside all the time. Yeah.
Would that be more development or would it be more design? like.
Well, it's all gonna be support in the beginning for everyone, and then you would have to move to a track of design. Design is usually a master's or PhD. Yep. Most time PhD. Like the design folks at Boeing, all PhD. Yep. All right, let's go through these. So I just found some decent kind of quotes or definitions of civil engineering is the improvement of civil society through the application of scientific knowledge. Civil requirements in today's society are focused on meeting basic human needs and assessing people in their daily lives. These needs are met by improving infrastructure and common utilities. So what is infrastructure? Roads, big time civil engineering. Like if we're going to develop roads, widen roads, if you come into road construction, some civil engineer has been involved in this. Sidewalks. So just transportation, bike lanes. Good. What else? Infrastructure.
Bridges.
Yeah, structural pieces like the bridges across rivers or creeks or anything else we need to go across for sure. So structural engineering is a subset of civil. So you get your civil engineering degree. That's focused on this land development, land use, infrastructure piece. And then if you want to go another year, you can tag your structural engineering license to that. Then you're capable of doing multi-level structures. Yeah.
So would civil be like ground foundation essentially?
Yeah, so civils can do the soil analysis under the foundation. Yeah, so a structural could do the foundation and the structural support of the building. But civil engineers will do a lot of land work. Like if this building was going to go in as just a bachelor's degree, civil engineer could come up with the necessary calculations to make sure the soil is supported. And where the rainwater goes is another big piece. So when you put a structure in like this, and even small structures now, city of Portland, right? You can't have rain runoff into the city. It's not allowed. So when you put in a structure in the city of Portland, you have to define where the water goes that would typically hit the ground. And that water's got to go into the ground. So a lot like we used to create septic systems in the ground with these long legs that allow all the water to go back into the soil. We have to do that with our runoff, our water runoff. So water catchments are huge in the city of Portland and required. That's because their old system can't support any additional water. Like as we get that, then we get the overflowing systems that pump into the rivers and create a big mess, right? Good. So do you think they're in the office very often? Yeah, so they're 50-50. I mean, just on average, 50% out, 50% in. The 50% out of the office can be like on a survey crew or surveying or getting that survey data, or they are the primary engineer for the construction build. So they're responsible that things get built according to plan out in a construction site that's dealing with a roadway or a waterway or a powerway, right? So when you go by some of these construction sites that are doing bigger pieces, you know, like on I-84 or I-5 or some of the bigger highways, you always see a group kind of off to the side standing around. That's probably a structural engineer, making sure that the side grades are at 30% or 20% or whatever they're supposed to be. So that's a constant check. Kind of subsets of civil, structural, geotechnical, that's the soil thing, environmental, wastewater, highway, mining, and transportation. So lots of different subsets and directions to go with civil. Yeah.
Is a mining engineer and engineer group divide like the mining aid or?
Yeah, so there's a lot of programs that are actually called mining engineering. So those are very focused. It's a big geotechnical piece. So if you're going to dig holes in the ground, you need to know what the ground structure is and what it's capable of supporting and how to do that without collapses. type of thing. So the whole geotechnical and the mining thing, that's the same thing in my mind. Yeah. They study soils and rocks and all the different formation in the ground. So you get a little of that in civil because you have to know, what soils will support. So when you put this structure here, that's a much different game than putting this structure up on Mount Hood. Because Mount Hood is all this soils and river rock and a different composition. So, or if you're going to set this down closer to the airport, for example, next to the Columbia River. The airport literally is below water level of the Columbia River. It sits below the water level. So there's a high moisture value in that area. So if you go to set this down there, you're going to need a different foundation than what it would require right here. So that's a geotech's job. Yeah, so it's common when you look at old structures, you'll see failing foundations or cracked foundations because corners are falling in here and there. And that's just because we didn't always have this consciousness of soil pressure. Like we just built them, back in the day. And now every region has its own soil pressures. So where I live, it's 1500 PSI. City of Portland, a lot of that's 2500 PSI. So those soil pressures are different based on where you're at. That's what civils can work with for you. Super important, especially on the structural piece. So, a lot of you will get your 4-year degree. Not many of you will get your master's degree because you'll just be done. You want to go to work. But at some point you might think about adding on to your degree because, for example, structurals, there's just not enough of them. So if you want to build something that requires a structural engineer, you have a heck of a time finding one, and then they're like 4 months out. So larger construction firms are going to have their structurals on staff, so they don't have to deal with that, right? They're just going to keep them on. So, all right, mechanical. By far the broadest. So a lot of times we find students that if they don't know, they choose mechanical. Just because it'll go into so many different areas. I'll explain that in a second. Improvement modification of mechanical components or machines and systems. This discipline of engineering uses principles of physics and math, which all of them do, so I don't know why that's in there, and applies them to the fields of machines and mechanics. So I like to say anything that gets manufactured, mechanicals will be involved with, and everything gets manufactured. So maybe not the structure itself of a building, but like everything that goes into the building, that's all gets manufactured. So you'll find mechanicals working, in the transportation sector at the Boeings and the Freightliners and the, automobile manufacturers, because there's so many machines within those facilities and there's so many mechanical parts that they need a lot of mechanics. If a company's making little multi-tools like Leatherman, they have many mechanicals on board, right? They're the ones that would figure out how that little multi-tool works, how it can be built, what it should be made out of, what materials it should be made out of, and how strong it's going to be, right? That's all the mechanical engineering. That gets handed off to a manufacturing engineer, which would then figure out how to make it. We need a punch here, we need a filing system here, we need a sharpening system here. Manufacturing engineer would do that layout and figure that out. Then when something doesn't work, the manufacturing engineer brings that problem back to the mechanical engineer and says, this doesn't work. Mechanical engineer says, well, that's because you guys are making it wrong. And the manufacturing engineer says, no, that's because you guys designed it wrong. And then they have their little fight. And then finally we decide to solve the problem. So yeah, there's a lot of back and forth there typically. And why is it so broad then? Like when the aircraft industry goes down and Boeing can't sell planes, mechanicals are not tied to the aircraft industry. They can go to the truck industry, or they can go to the microchip industry because there's a lot of machines at a microchip facility, right? They can go into the medical industry because there's a lot of mechanical engineering machines in the medical industry. They could go into large construction because there's all kinds of mechanical engineering processes in a large structure, like the heating and ventilation and air conditioning. That's all mechanical engineering, right? How this room gets heated, how this room gets cooled. You know, what makes it cool or hot? That's all mechanical. So they can go into all these different industries where civils are more locked into infrastructure, land development. So when we had the housing crisis, civils got hurt a bit there. They lost positions because we just didn't have any work. There was no large contracts. There was not much going on. So they're more focused into a sector. Mechanicals are more kind of wide ranging.
Earlier on the list of the different disciplines, you have manufacturing up there. What discipline would that fall under?
Mechanical for sure, right here. Yep. So here's mechanical subdisciplines, and there's more, but thermal fluids, so that's heat fluids, heating and cooling, automotive, machine design, aerospace, nuclear, manufacturing, HVAC, right? Anything that deals with temperatures and the control of temperatures is going to be more mechanical. So that's why nuclear is on there, because nuclear's got an enormous amount of heat going on and needs to be dealt with. So there's also nuclear engineers that are dealing with the actual nuclear, fusion and fission, that kind of thing. But mechanicals would be like an early child to a nuclear engineer. So Oregon State has nuclear engineering, and you go through the mechanical engineering program first, and then you can join the nuclear program. Good? Questions? No? The other thing is, like, when you go to school for mechanical, you take some crazy class, like just a crazy array of classes, where civil is much more focused, on your civil engineering, but mechanicals, we take all of this. Like, we take machine design, we take thermodynamics, a lot of it, that's heat transfer. And then we get into the manufacturing lab and understand those manufacturing tools. Then we do the heating, ventilation, air conditioning, we go through all that stuff. So we have electrical power system classes. It's just very broad, super broad education. Where do you go to work? Defense, large manufacturers, consumer products, automotive, marine, anything that's made. That's where you can go to work. Dollhouses, trailers, you name it. Was that also for, yeah, right here, job sectors. So this is the job sectors for civil. You see civils, a lot of new civils go to municipalities. City of Portland, City of Gresham, City of Sandy, right? All of these, City of Bend, all of them will have civils on board in their city planning department. Just lots of municipalities. And lots of government agencies. The Forest Service loves civil engineers. Army Corps of Engineers, that's all civil engineering. Electrical. Electricity and electromagnetism focuses on both small and large scale electricity requirements. So you'll find electrical engineers working for a large, like, electrical contracting company. So if you had a big electrical contracting company, the kind of company that would work, on a building like this, designing the power grid for that, you're going to find electrical engineers. Not on a small, electricians, not electrical engineers, not needed. Yeah.
That's what I was gonna ask.
Yeah. No, absolutely not. Yeah. They learn electricity, and they learn how to manage electricity at the lower voltage levels. So, most of the time it's 240 volt and below coming into a home, and that's what an electrician is going to work on. Some electricians will do some commercial work, but that's like a next grade of electrician, but they're not designing it, right? They're just installing, managing it, making it work type of thing. If you're going to design it, then you would be an electrical engineer. Build those structures. Yeah, so you find them obviously in any kind of power development, you're going to get electrical engineers. Any kind of microprocessing, electrical engineers, because it's both little and big electricity that they study. So they can design those circuitries within a microchip, for example. Electrical engineers could focus on that, which is pretty complicated.
Do electrical engineers get paid more than electricians?
Yes, for sure. Yeah, although electricians are getting banked right now, so I would wonder if that's true. Like, I think their billing rates like 120 an hour now. So that's pretty good wages. But it's kind of a different game because electrician is going to be an hourly wage. Electrical engineer is going to be a salary wage. So wherever you go to work, and most of these mechanicals, that's going to be salary. Civil, that's going to be salary, meaning you're going to get paid so much a week. And then it's pretty much whatever it takes to get the job done. Some companies are worse than others with too much work type of thing. Some industries are worse than others. So if you're going to work at a large company, that's going to be controlled, right? There's just going to be a lot of controls in place. You go to work in a smaller company, like a construction company, the construction industry is pretty crazy with its hours. Like they're full on when they're full on, and then they're pretty slack when they're slack type of thing. So it does depend on the size of company you go to work for and the industry. Yeah, you can read that. Power grids, computer circuits, software programs, power supplies, micro to big, telecommunications, all of that, electrical engineers. Very sought after, not many, I think we did a hand raise in the beginning and there was just a handful or less of you that were electrical. So not a lot of graduates compared. Mechanical, bazillion graduates every year, right? So you had some competition to get your job. But electricals, not many graduating per year. Yep, and civils and energy also. Yeah. So like, for example, just a second, big wind turbines, very civil structure. Like that structure of a wind turbine, that foundation mount, that long column that holds the turbine, civil engineering, and the layout of the grid, that's land development, so that's civil. But electricals are big time in that. Yep, question? You had a question?
Yeah, I was thinking electronics engineering, which is like, is that kind of electrical or?
I would think it would be an electrical, but I don't really know. That's pretty specialized. Pretty specialized. Jobs, right? So telecommunications, power generation for sure, software design, sound, renewable energy, anything that uses or produces electricity, double E's are going to be there. And we have a lot of things using electricity and a lot of things producing electricity. So chemicals. So transform raw materials into useful, innovative products for public and commercial consumption. So metals, gases, right? Fuels, drugs, construction materials, all chemical engineering. Most chemicals in this area are going to deal with petroleum products. So we have a big refiner right downtown Portland, Phillips 76, big refiner down there. I think they have 7. I have a friend that works there as a safety supervisor. And he said that they have 7 chemical engineers down there. So lots of work in the refinement of fuels in that industry of, oils and lubricants and all that stuff. But they're in these other areas, drugs, construction materials, if you're going to use a carbon fiber, that's a chemical engineer that produced that mix to come up with that strength, to come up with those materials, bring them together appropriately so they bond and you have a good building material. So we use those quite a bit. Plastics, all of that stuff. Chemical engineering. Mining, mineral extraction processing, petrochemical, that's your fuels, food production, and pharmaceuticals. Drug developers. drugs of the good kind, I'm hoping, but
Related to chemistry, I mean, like, it's obviously.
yeah,
but You take a lot of chemistry.
you do.
classes.
Yeah, you're like chemistry on steroids. It's remarkable. So, if you've had a chemistry class and liked it, then that's a good thing. If you had a chemistry class and hated it, then
So
Yeah.
that means that there's chemistry classes and then like industrial chemistry, is that the difference? Or
so I think they're more focused chemistry classes. So I think your early chem 221, 222 are kind of like just spraying content at you. And then your third and fourth year, you would be more focused into probably a chemical slot, like material chemicals or pharmaceutical chemicals or those kind of things. Yeah. Good. And then computer science, I think this is the last one I'm doing. Computer science, you probably all can figure that one out. So design, implementation, management, information systems, both hardware and software. Lots of software in computer science. Some electrical is in computer science, so you get quite a bit of electrical engineering content within a CS bachelor's degree. But a whole bunch of coding, right? You would just be coding like crazy. Both writing software, understanding software, and debugging
what
software.
would be the difference with just a general computer science degree?
Computer science, bachelor's degree? Yeah, no, that's what this is. Yeah, that's what this is. Yep. Yep. And I think, let's see if there's. Yeah, here's a job sector. So that often will help you kind of understand what's in the program. So, app developer, software tester, cloud computing, compiler design, software engineer, all of that within computer science. So I would guess this has a bunch of choices and flavors that you could flavorize your computer science degree. That's my guess. Mechanical is that way too. Like when I went through mechanical engineering, we were encouraged to have, a second focus within the program. And that's just additional courses that you choose to take. And if those are all flavored the same, then you can call it your minor, basically, in engineering, right? So I was really interested in structural materials and trying to just understand all the different structural materials. Well, we had a strength of materials class, goes over a few of them, but like it didn't get deep into composites, or it even didn't get into exotics like titanium and that kind of thing. So you can choose those courses that are in addition to your degree and build a minor. And that's a really good thing. But you're also then building a focus, like that's probably where you're going to go to work in that direction. So it's a good thing, but it does focus kind of where you apply. So I would guess, I bet CS has a bunch of branches type of thing. Like civil has a structural branch, right? I think civil has a geotechnical branch that you can go into, but then that's about it.
Yeah, so which engineering has the most jobs?
Be mechanical just because there's just more availability, like more places you can go to say, hey, I could apply for that job because I'm a mechanical engineer,
What
right?
about civil?
So civil's going to be pretty good in Oregon because we still have a lot of land to develop and we do a lot of developing still. So you go into states that are a little more dense, like on the East Coast, and there's just less development, but there's also more retrofitting and that kind of stuff. So, yeah. There's a lot of opportunities in each. There really is. We just don't graduate enough engineers each year to fill the slots. So if you can get through, you're going to be pretty set. And even with the whole concept of C's get degrees, like get through. Doesn't have to be A's and B's. Be better if it was A's and B's, but yeah.
So for biomechanical engineering, for subcategory, would that even get detailed into bionics? If I wanted to do something that's like designing.
I don't-
manufacturing?
Yeah, so I don't know a lot about that discipline. Like I don't know all the sub-disciplines to it. I don't think there are a lot of them. I think there's fields of study after you get through. And I think each discipline's that way too. Like if you're a mechanical engineer and then you go to work at Freightliner, you've chosen kind of a path, right? You're in transportation. And that's where you're going to get your first experience. That's where you're going to build your skill set in the beginning. So just based on the company you go to work for, you're kind of slotting yourself into that industry. Not that you can't move out, because planes have brakes also, right? So if you're doing brakes at Freightliner, you could become a kind of a brake mechanical engineer, right? Where you're really good at setting up brakes. You understand heat transfer of brakes. You understand all the different materials involved in braking. You can take that knowledge into any industry that has that kind of function, right? That has braking. So you're not completely stuck in the transportation, but you might get slotted into a discipline just by the job you take. So, yeah.
What would you say the difference between an architect and an engineer?
Oh my gosh. That's huge.
Like,
Are there any architects in the room that want to be architects before I slam you? No, you're all good? Okay, great. Architects design the use of space. That's it. That's harsh. It's important. I designed my own house, right? And I have no coat closet by the front door. Because I'm like, I never thought of that. That would be nice now though, because when I come in, I got nowhere to put my coat and everyone throws them everywhere over the railing, right? So I designed my own home and it has a number of mistakes for the use of space, right? We have small bathrooms because it's not a priority to us, but when we go to resell, everyone's gonna go, man, your bathrooms suck because they're not like 4 sinks like they do now or whatever the heck they do, right? So architects, they design space. Then they take that design and they hand it to an engineer, and an engineer like goes, holy crap, I can try to design that, right? And then there's just a little back and forth, but yeah, and they're architects very good at what they do. Like the spaces they design are not only aesthetically beautiful, they're also a good use of space. Like the traffic flow is good for people, the usability is good, all of that, but they can't design the structure. If some are better than others and they've, taken classes and they actually know that a beam can't span 84 feet without some supports, without being giant, right? So,
often heard the like, quote, an architect's dream is an engineer's nightmare.
yeah,
Is that wrong?
very true. I'm experiencing that now because architect designed what I'm building for this family, and it sure looked good on paper, but to make it reality is not that easy to do. So, yeah. So I think and they go through just a floodload of school. Like it's it's more than 4 years to get your architectural degree. It is. So it's unbelievable that they draw that many pictures for that many years, but that's what they do. They should do some engineering. Oregon State just started an architectural engineering program that's really good. And it is an engineering degree. So those architects, so that's just taking an engineer, which is normally really square, like just square designers, not aesthetic, just like we can put some posts up and some beams and it'll work, right? And it looks like shit. Like that's kind of like this place. It's like a cave, right? Not a lot of architectural flair to this building, right? So the Oregon State program combined architecture with engineering. So there's a lot of construction companies that really want them because they can do both pieces, one person, both pieces, right? So that's a nice program. All right. Then just a real little, blurb on what we do and how we do it. Okay, good. Any questions on that? Yeah.
Program that was like 5 years, and you could get like a bachelor's in civil and forest engineering.
Yeah, there's a lot of cross degrees. Yep.
What was that? Like, that forest.
So if you want to be a forester, that's a 4-year bachelor's degree in forest engineering. So it's a hybrid of civil because they do a lot of roadways. Like forest engineers often are just, how are we going to get the equipment into the trees and get the trees out of there? Like, where do we got to build the roads? We just can't go straight up because log trucks just can't do that. So, where are the contours and how do we build the road in there? That kind of thing. When John comes and talk, he was a civil engineer for the Forest Service, so he can talk about forest engineering. But it's kind of a heightened sense of the environment also now. So civils are gonna also like, okay, we can't just build that road right through that creek like we used to, right? Now we have to like do it correctly and not impact that environment type of thing. So they get, I think they get an environmental piece in there too. And then they get a lot of standard engineering, so. That's all I know on that one. Yeah. Yeah, look at degrees and then talk to people that are in them and see why they chose, you know, what's up with this? Why'd you do this? All right, now. Yeah, I want to do some force stuff for you. So you have the problem definition coming up, right? That's due Wednesday. Then after that brainstorming, those two are pretty similar. When you do brainstorming, you kind of break it down into brainstorming. When you do problem definition, just focus on the problem. But before long, you're gonna do some calculations on your project. So I need to arm you with some ability to calculate. So I'm not going to give you like statics and strength of materials and dynamics in 1 hour. That's not going to work. So I'm just going to focus on the ability of a structural piece and a simple structural piece. So after I go over this, you all are going to go like, well, what if I use this shape? I'm going to say, well, that just makes it a lot more complicated, right? So when you do your calculations on your project, which I want you to do, I want you to forecast or estimate if you think it's going to work based on a calculation. That's the goal. Okay, you're going to probably use trial and error as your primary tool, but it's, you know, before you get done with the project, I'm going to have you calculate and try to estimate whether you think your structural piece is strong enough or not. All right, like I said, trial and error testing will probably be your best tool. Okay, so one of the simple things we can do is try to understand how the forces are on just a simple beam, and then how those forces get carried by the material. So when you load something, that load that goes into the material or into the system, the material carries that load. If it does carry it, then everything works just fine and nothing moves, type of thing. If it doesn't carry it, then something fails. And we don't want that. So what we have to be able to do is kind of understand like how do loads get inside the member itself? And then how does that member resist it? Okay, what's the strength of that thing? All right. We are going to go to this. All right, so what we're going to focus on is just basic standard bending. So the bending of, oops, dang it. That was the wrong button. That's all right, we can fix it. That's the right button. So we can predict on our system, assuming that we have some kind of structural piece, we can predict how much bending is going on, and then if the thing can resist. Okay. So the way we do that is with the bending stress equation, and I have simplified it. It's in the simplest form that I can come up with. So the bending stress equation, S sub B, stress bending, you'll find that some classes will call this a Greek letter. Some classes will use S for stress. Some classes will even use different symbols. So that is part of the game of engineering, is to try and understand what symbols are being used in the class you're taking. Physics might use something different when they talk about stress, right? Statics uses something different when you talk about stress, and then strength of materials uses something different. That can be a book function, like that author likes Greek letters. That author likes the alphabet. There's no rhyme or reason to it. I'm going to use S for stress. I'm not going to use Greek letters yet. And the equation is MC over I. So we need to define these three. And that's going to give us bending stress. So when a structural piece is under load, it's loaded. Often one of the stresses that we think about and that we design with is bending. There are other stresses going on. There are tensile stresses, there are compressive stresses, there are axial stresses, there's torsion, rotation. So there's much more than one thing. Well, I'll make that clear, but we're just going to use one thing as our predictor. Because if it can hold in bending, that's a good thing. It might fail in something else, but we don't know it. Okay. A lot of times you design in bending. So bending is a very common stress that you design in bending and then check it in torsion, check it in shear, check it in compression, check it in tension, check all those other stresses, but design it in bending. So that's why I'm choosing to use bending. Okay. The units for bending stress, PSI. Anyone know what that stands for? Pounds per square inch. It's a pressure. So sometimes you're like, pounds per square inch, that's like my air compressor, there's 100 PSI in it. It's a pressure, but it's a pressure that the material's feeling. The structural material feels this pressure. The ground right now feels pressure from the building, right? Fortunately, the ground can fight back with that same pressure and it's all good. So that's what we have to figure out is like, how much pressure is on this structural member and how much can that material fight back? So the amount of strength in a material is called the material properties. The materials have a lot of properties. They have they can conduct electricity or not. That's a property, right? Wood, not so much good at conducting electricity. Pretty good at carrying a load because it's light and cheap. That's why we use wood, light and cheap. So there's a lot of properties, right? We're only going to focus on one, and that's this bending stress thing. But they have other properties. Like wood's got a property that's not so great. It's alive. It's growing. You cut a tree down, made a 2x4 out of it, and then deliver it to me, and I look at it and go, geez, this thing's still growing. Like right now it's growing, and in a year it's going to be like 20% reduced because it's going to dry out and get smaller, right? So wood's not great on that thing. It's like still growing. It's organic. Once you use it, it starts to die. That's not a great material. And then it's got like all these imperfections in it, like knots and holes and, all kinds of grains in it. And yeah, it's an interesting material, but it's cheap. All right. So the bending stress material property for Douglas fir, it can carry 1050 PSI in bending. 1050 PSI. Kind of sounds strong, but if you compare it to steel, 36,000, well, it's much different. Magnitude's different, right? So we get these from industries that have this information for us. Okay. Lots of information out there. There's wet Doug fir, there's dry Doug fir, there's kiln dry Doug fir, there's, Doug fir #1, there's Doug fir #2, there's a variety to this. I'm just choosing the 1050 PSI, the most common one. The good news is the factor of safety has already been built in, so you can use that directly. So factor of safety means like, okay, well, it doesn't look like a perfect material. I bet all of it's not 1050, right? So they've already done all of the reducing and all of the changing necessary for you to use that number directly, 1050. That's a nice thing because the rest of the materials, you don't get that luxury. When it comes to you, you have to apply your own factor of safety based on what material you're getting. So, all right. So what we have to do is we have to figure out these three variables, MC and I, and then we can calculate a bending stress. And our calculated bending stress, we compare to the material. So the material property for Doug fir is 1050. That's our target. If we're below 1050 when we calculate, we're good. It should work, right? If we calculate over 1050, then it's like, something's not good. It's probably not going to work. Yeah.
So exceeding the limit, does it bend or break?
Great question. So failure for almost every industry is a unacceptable deflection. So it's not breaking, but it's deflecting unacceptably. Like that's too much. So like when you walk into a home and you walk across the floor and the floor goes, just from you walking across it, the floor bounces. Older homes do that because we didn't have any control over deflection. We just used the strength of materials. It's not going to break. Like you can get 10 people and bounce up and down. It's still not going to break. Just feels like a trampoline, right? That's unacceptable now, though. You can't have that much deflection. You walk across the floor, it's got to feel solid. So deflection should typically in a structure be low. Yeah, you don't want to look up and see this concrete ceiling kind of going like this. That's going to be bad. No one's going to be comfortable. Huh? For what? 1/300th of the span. 1/300th of the span. So if the span is 10 feet, you take 1/300th of the span. That should be the allowable deflection. That's just a rough guide, but we use that quite a bit. All right, so let's figure this out. Here's my beam right here. I don't know if you all can see it or not. It's made up of wood. I have it in the flat position, so it's made up of wood, right? It's glue lam, 3 things glued together. Doug fir. Could be like hem fir, which is hemlock fir, right? When we put it here, we have a big span, and we'd like to know, like, how's this 6.5 pound weight going to work in the middle of that? In that position, in the middle of it. So let's go through the variables, because we have to figure out like what these variables mean. So we have M, C, and I. M is moment. So in the engineering world, we call it moment. In the automobile world, it's called a torque. So if I said torque, more folks probably would understand what that is. Torque and moment, same thing. It's a rotational effect. Well, our beams, they're not rotating. So we have to figure out like, what's that mean, right? What are we talking about there? So moment, the unit of moment is foot-pounds. And the way we get a moment, the best example is like, I'm just going to fix that point right there. So this is a pin. And this is a force of 100 pounds. And this is a distance of 2 feet. Okay. So if we have a force at a distance, that force is trying to rotate around a point. So I'll call this point A. Everyone agree? It's like a wrench. Like if you've ever put a wrench on a bolt and pushed on it, you're creating a torque. That's how you take the bolt and tighten it or loosen it. Screwdriver, same thing. Okay. So the way we calculate it, a moment is equal to, force times distance. So how much is my force? 100 pounds. How much is my distance? 2 feet. And that equals my moment. So what's my moment equal to? 200 foot-pounds. Foot-pounds. No per, no feet per anything. Foot-pound. Yeah, foot-pound. So that's how much torque's going on that point right there. Everyone kind of understand that? Now I'm going to apply it to the beam. Okay. If I put a load, I mean, this is kind of the load condition that we have in front of us. We have simple supports on both sides, and then we're going to put a load in the middle, right? This is called a simple beam. Simply supported on both ends. This is called a, anybody know? Yeah, cantilever. Cantilever. Only supported on one end. So if your plan is to take the eggs, and attach them to the end of the pole and get it over there, that's a cantilever beam, right? If your plan is to take something and land it on the table and then get your eggs across somehow, that's a simply supported beam because it's supported on both ends, right? So we can think about both these, but what's going on is when we apply this to the center, this force is trying to rotate around that point. because this point is fixed. It's not going to move on the table, right? And it's also trying to rotate about this point. So it's trying to create these rotations, and that structural piece is trying to say, oh, no, 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 you're not rotating. You're staying right here in this spot. Yeah, so if I put the weight here, what's trying to happen? And I have this as point A, and this is at point A. Yeah, so it's trying to rotate around point A, and this piece is saying, no, 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 don't rotate. Yeah, so that's at the microscopic level. Yeah, so pulling strength is called tensile, right? So when something bends, it's kind of fun to talk about, at least for me, right? So when something bends, so here we always exaggerate bending like that. So we got our support here, we got our load here, and then we have this beam that's bending. And if we look at that beam kind of microscopically, what's happening up here at these fibers? Yeah, they're being pushed together. They're being compressed. So we have compression here. So we have a compression stress here. And then what are these trying to feel? Yes, pulled apart, that's tension. So that's a tensile stress. We're not going to go to this level on our beam, but that's what's going on. And when something bends and then breaks, these little fibers pull apart. That's how it breaks. Once those pull apart right here at the outermost fiber, then it's just like a zipper, right? Just pull, completely busts out. So that's why when you cut a branch off, it just falls over and those bottom fibers stay together and the branch doesn't fall because you didn't cut through those. Hate that, but it happens every time. Branch attacks your ladder that you're standing on. Don't do it. It's dangerous. All right. So moment, force times distance. If I have 6.5 pounds and my overall span is 11 feet. That's what this is, 11 feet. Oh, sorry. Overall span's 11 feet and my weight is 6.5 pounds. Yeah, so be careful here, don't calculate yet because we have one more step. The part of the beam that we're most worried about, where would you think that is? The middle. Yeah, this beam, sorry. Yeah, good question. This beam, the middle, this beam. Yeah, right at the support. That's where we're worried about the most. So you do your moment at the location that you're most worried about, right? Where's the failure going to occur? And I've given you some simple loading conditions. So as the loading condition changes, it's a much more complicated problem. Yeah.
So why don't we use, where does gravity benefit this situation? Because
That's where we get our load. So this 6.5 pounds is being created from gravity. So this is not a mass, but this is a mass times acceleration to get pounds. Yeah. So that's where gravity comes in. But where does the weight of the beam come in? Well, it comes in right here, but we're ignoring it. Right? But you would typically include the weight of the beam because I think this thing's actually
it's
like sagging under its own world, right? It's like can't even hold itself up, you know, on 6.5 pounds, but we'll see. Yeah, maybe. I think it's permanently bent. Yeah, it's a typical piece of wood. It's not straight. What are foot pounds? It's a torque. Depends on what class you're in. I just taught fluid mechanics and it's energy there. Foot pounds are energy, right? Foot pounds over time. So if you say 450 foot pounds per second, that's a torque per second. That's an energy module. That's energy. So it's the foot pounds are, it is a rotational effect is what it is. Okay. Instead of a linear effect, like the 6.5 pounds, that's just a vector going straight down. It's just a load, right? But a foot pound, it does this. It rotates. It's a curly vector. All right, just stay with me. So if this is the spot we're most worried about, and if this is a system in equilibrium, there's a load here and a load here, right? Because we want it to be in equilibrium, which means it's not going anywhere. All the forces are equal to 0. So 6.5 down, how much are these two going to have to be to keep it in equilibrium? 6.5 total. Yeah, 3.25 and 3.25. Yeah, pounds. Because the forces up and down have to be in equilibrium. That's how the building sits here, right? The ground's pushing back up.
So essentially they have to be
In a simple system with a load in the middle. This load moves off to the side, game over, we got to calculate.
it has to be able to hold.
It has to be able to hold half.
Yeah.
Yeah, absolutely. That's what this thing is doing right here. The weight of the beam, right, is being applied over there and over there. We got the nothing in between. So whatever that beam weighs, there's half over there and half here. That make sense? All right. Now we can get the moment here at the part we're worried about. So the moment here doesn't have to do with the 6.5, has to do with the 3.25 times the 5.5 feet. Because we want to know what's going on at the middle, right? We want to know what that's happening at the middle. This thing is being applied to the middle. So if I did the moment of that, it would be the force times 0, no distance, because I'm at the force, right? So I use these forces. I don't use them both because if I did, they would counter each other. I just use one of them. So the moment on this system is one of these times the distance. Yep. So the moment for this one is 5.5 feet times 3.25 pounds. I'll call it point B. What do we get? No, it should be 5.5, should be just over 15.
So it should be 17.
17.875 foot-pounds. If you're not calculating it right now, then you're just trusting him. Just saying. If we got 10 people calculating and we all go, oh, we all get 17.875, then as an engineering firm, we're doing better. All right, remember what we're trying to do. We're trying to get M, C, and I so we can calculate. Right? We have M. Others get this number? Yeah, okay. We have verified. So for our first beam, this one, we have a moment in the middle of 17.875. You want to find the moment at the part that is going to be the failure, the highest loaded part. Yeah, I'm just giving you that information. You just got to believe me on that one. Yep. And for a cantilever, it's going to be right at the support. Yep. Questions so far? So that's like the force on this thing. Yeah. I made that my point B. Point. Yeah, we label all our points are labeled typically so we can refer to these things as we calculate. Like, where are you calculating this? Right, is what somebody will say. If you don't have like moment at B, force at C, you know, so we're all talking the same thing. All right, so we have C now because the equation is MC over I. Okay, we got M. It's a foot-pounds, it's a torque. C is just a distance. C is pretty easy. So looking at the cross section. Cross section means like you take a knife and cut through it, right? You look at the inside. So looking at the cross section of your structural piece. So if it was a pipe, your cross section would be round, right? If it's a rectangular beam like this, your cross section is rectangular. If we were smarter, the beam would be on its edge and our cross section would look like this. Correct? So it's the position of your beam when it's loaded. And the C distance is from what we call the neutral axis. It's really the centroid of the shape, the geometric center of the shape. So rectangle is pretty easy, like it's just halfway, right? And the C distance is from that axis to the outermost fiber. Outermost fiber, just straight. Okay? It's the largest distance. Notice I put two C's. I put a compression C and a tension C. But a rectangle is symmetrical, so they're the same, right? But there are shapes that are not symmetrical. So if your shape is not symmetrical, you want the largest C value. Yeah. Doesn't stand for anything, just stands for distance. Yeah, just distance. I don't know where they came up with C. Where'd they come up with moment or torque? Like, why not just use torque? I don't know. But yeah, no, it's just a linear distance in inches or feet. Right? So this one, notice, has a larger C value, same beam, just in a different position. Our position's here. Okay. So you just have to know your cross section, and then you have to know where the centroid is. So if you make a crazy cross section, you got to figure out the centroid. There's equations for that. But just for example, like an L shape, right? An L shape. Here's the neutral axis or the geometric center. So it has a different C value. I'll call that C compression, and I'll call this one C. Actually, C compression, C tension. Sometimes you'll see C1, C2, doesn't matter. But you're looking for the largest value. Okay. Our structure is 3/4 of an inch. Top to bottom. So what's our C value? 3/8 of an inch. Half of the 3/4 of an inch. Okay. So C value. Anyone know the decimal equivalent of 3/8? 0.375. Oh man, we're getting there. We have M, we have C. And it's just inches or feet, right? We have to make the equation work to give us PSI. So I might have to massage these feet later to get it into inches, but I'm just going to leave it for now because we have one left to get. That means inch, right? This means inch. Or you can write inches. Yep. Cost for use feet. Yep. Good. Hang in there. Now we need I. Yeah, I is the trickiest of them all. It's called the area moment of inertia. Area moment of inertia. And it has to do with the cross section. Cross section. So each cross section has different properties, make them strong or not strong. So we have cross sections that are not very strong, and then we have cross sections that are really strong. Okay. I helps us figure that out. Yeah. C is the distance from the neutral axis or the center line to the outermost fiber. It's just a distance. Okay. That's it. So it's here it is in this position. This is a different position, right? This is flat. This is vertical. Okay. So I has got a formula for different shapes. And I know the rectangular shape. I equals base height cubed over 12. So again, it is the cross-sectional shape that helps us understand how strong a beam is. It's pretty cool. We haven't talked about the material at all. Like M, we didn't know it was Doug fir or whether it was titanium, right? C, we don't know what the material is. It's just the shape of the material that matters. And now I, it's just the shape, nothing to do with the material
So it helps to find the strength.
of the structure of this thing. Yeah. Did you have a question?
Just like we're figuring out how much the beam and bend
Yep.
and the material and like the dimensions around that would change what like max stress load would be. We're just figuring out how to figure out.
Yeah.
what the
We're just trying to
articulation-
understand how to come up with the bending stress. Right? But it's interesting, it's bending stress is not developed from the material. Yeah, so we're not even thinking that this is Doug fir. There, at no point has we said, hey, this is Doug fir, because we can calculate the shape's strength. And that's what you do, is you calculate the shape strength and you compare it to materials. So you got to know what your material is to know if that's going to be safe or not, but we're just really calculating the shape. And the load's important. All right, so here's the equation, base height cubed over 12 of your rectangle. So each shape has its own inertia equation, right? If you did a round solid, that's an equation. If you did a round hollow, like a pipe, that's an equation. If you do a triangle, that's an equation. If you do an L shape, that's a different equation. So you can look these I equations up for different shapes. I just know the rectangle one and it's one of the simpler ones, so that's why I chose it. And I have a rectangle, right? All right, so let's calculate this. What's our base? I don't know. Let's measure it. I'm guessing it's 3/4 times 3. What is that? Inch. Yeah. 2¼ right on. So we are 2¼ and we are 3/4, right? So that's base height cubed over 12. .25. Height is 0.75. I don't trust any of you. Plus, it's like therapy to run your calculator, isn't it? Really is. Get it kind of fast. Hopefully somebody agrees. 0.079. I equals 0.079100102 inches to the 4th. What a weird unit. This is inches. This is inches. Anyone tell me what inches to the 4th is? Inches to the 4th. What is inches squared? Area. What is inches to the 3rd? Volume. What is inches to the 4th? Yeah, some time and space thing. I don't know. The engineering books will say it's just a mathematical quantity. Just leave it at that. Just like move on. Don't think about it too much. Yeah. What I can tell you is inertia is an indicator of stiffness, resistance to bending. The higher the inertia, the more resistance to bending you will get out of your shape. regardless of the material, right? Doesn't matter about material, it matters about shape. So the higher the inertia, the better. So how's ours looking? Sheesh, not good. What would the number be if we actually put it in the strong position? Like I have it in the weak position. What if it was in the strong position? Yeah, so in the strong position, it's going to be I equals, and everything flips. So it's 0.75, 2.25 cubed over 12. That's in the strong position. Run that number with your fancy pants calculators. Formula is the same. If you just put different units in, you get those units to the fourth out. Just don't cross units in the equation. Oh, no, it's, yeah, millimeters, same formula. Yep. Anyone else get that? 0.7119?
Yeah.
Yeah. Still seems kind of small, but it's what? It's like magnitudes bigger than that. Lots bigger than that. Okay. All right. So now we have I. Inches to the fourth. Yep. So now we can run our bending stress. What was our moment? And what was the unit? Foot-pounds. And so it's MC over I. What's C? 0.375 inches. Is that true? Hang on, let's get this. Make sure I didn't make a mistake here. That's good? Okay. Yep. Go ahead. Question.
Are we going to translate the 17.8?
We are. We're just going to get it all built first and then make the units work. And then what's our I value? (9,102 inches to the fourth). Yeah. And the units we want out of the equation are pounds per square inch, PSI, right? So pounds are here, that's good. Feet, that's not gonna work. We got to get rid of the feet. Because we got inches and inches, that's good. Okay. So how do I convert this number and get rid of feet and put inches in? I have to put that conversion in, correct? So we know that there's what? 12 inches per foot. And we can write that in fractional form, but we want the feet to cross out, right? We want the feet to go away. So I'm going to write it as 12 inches per foot, 1 foot. That makes sense? So you write it kind of, so it does this multiplication and then the feet will cross, right? And we're left with inches, inches, pounds, and inches to the fourth. Yeah? Everyone okay with that? What happens to these 2 inches? They become inches squared. And we have what down below? Inches to the fourth. So those can cross and we're left with inches squared on the bottom. Unit analysis. That's called unit analysis. We do it with everything. Okay? So this should give us pounds per square inch. Yeah? All right. Calculate that for me. That's our bending stress. I'm doing it too. I don't trust you. Anyone get a number that they're proud of? 1016.88. Yep. PSI. Outstanding. You just calculated your first bending stress. That's super cool. So, what was the allowable stress for Doug Fir? 1050. And what's our calculated stress? 1016. So just make sure you got that clear. Like you calculate a stress, there is no point of doing that unless you're comparing it to something. Otherwise, you're just like wasting your life. Calculating stress all day long, that's great, but you got to be comparing it to something. Like, why are we doing this, right? So that's our prediction, 1016. The material limit is 1050, but we know that limit is just in bending. That's not a failure limit. That's an acceptable limit. Okay. All right, let's test our. That's what I want out of your project is I want you to like make an estimate like, hey, based on these calculations, this should work, right? I should be able to put it in the middle and it shouldn't go to the floor. What do you expect? Expect it to work, but to be what? Like right at the limit. 1016 compared to 1050, that's like right there. Okay. So, all right. I didn't measure the middle, just guessing. There we go. It didn't fail, but it kind of failed. There's a lot of reflection.
We have to take into
It might not be acceptable, right? But it didn't fail.
So then, how would we take into how would we take into factor reflection?
Get a 4-year degree, because keep going to school. Keep going to school, you'll get it. So there's deflection formulas, and we can calculate deflection. Right? Yeah, so what happens is, so what you did is you calculated the calculated stress, right? That is the easiest thing for me to teach you is like how to calculate a stress based on the load. Now, once we take this away, we want to say, okay, we would like this not to deflect. How much load could it take? That's a whole different equation. It's like working it backwards. We set the 1050 to the equation. We leave M unknown because that was our load. We have the same cross sections, so we still use C and I, but M becomes unknown, and then you work it backwards. But it's definitely more simple. Okay. So the other thing is you can do the same thing with it in this position. Right? In this position, what's our bending stress? Let's do that real quick and then we'll be done. So now I've put it in the strong position. First one was in the weak position. So what changes? C changes. Absolutely. Does the load change? No, we're going to use the same load. So this whole moment thing is still the same. It's going to go in the middle. But now C changes, and does I change? Yeah. Yep. So now let's put in the strong C value. That would be this value, which is what, 1 1/8 maybe? 1.125 inches. And then we calculated a strong I value. That was this, I think, right? Yeah, this is the strong. So I wrote the wrong one in there. The first one should have been. What'd you guys use for the I in the first one? Anybody? It should have been the first inertia we calculated. Was that this first one?
We never wrote down.
Oh, we never wrote this one down, the strong one? Okay,
We
good,
wrote that down next
good,
to
good.
it,
So this
but
was right. Okay, good. Oh, yeah, it was like 0.7 or something. Yeah. So this would be weak. And then this will be strong. Yeah, I get 0.71191 inches to the fourth. Anyone get a bending stress for the strong position? I got mine. This is gonna be the I right here. C is gonna be 1.125. Because now we're in the strong position. And M's gonna be the same, but don't forget the factor of 12. You tell me. The bending stress I get is why'd it go down? It's a different shape. It's a stronger shape. Okay. So remember, we're just doing a calculated stress based on the load and the shape. So the first shape was in this flat, weak position with a low I value. Right? The second shape is in a strong position with a higher I value, right? Higher I value is going to drive the equation up, but drive the equation down because it's in the denominator, right? Big numbers in the denominator drive it down. So we get a lower calculated stress. No, that means in this position, we compared the 338 to what? What was the 1050? Yeah. So 338 compared to 1050 were magnitudes under the stress. It puts less stress. It's telling you that, hey, there's less stress on the system when you put it this way, right? You put it this way and you load it, there's lots of stress. You put it this way in the strong position. Stay. I'm not sure it even did deflect.
It did, it may be just a little, right?
Was the 1050 change at all?
Same material. Remember, the 1050 is based on the material. So as long as we didn't change the material, then we don't change that. That compares, right? Absolutely. Yes. Yep.
That's where you kind of have to figure out.
So here's probably the big thing. Bad I value. It's not supporting a bending. Low I values just do not resist in bending well. High I values resist bending really well. Yeah.
The break is just to demonstrate, to break it all.
We did because the M, remember, yeah, it was part of the load, the M value, yeah. So the bricks like your X, that's your load you're kind of dealing with, right? So. Yeah. All right, that was a lot. That is it. So the other reason I do this is you're looking at 4 years of this kind of a class. Like this is what we like to do in all of our classes that in my mind that have meaning, right? So when you do your statics, your strength of materials, your fluid mechanics, your AC/DC systems, this hour, if it took me an hour, is very much like what we'll do day in and day out, all the way through your college life. Like that's kind of what we do. That's our tool in our toolbox, right? And it gets overwhelming. Like sometimes like you get halfway through it and go, what the hell are we doing again? Why are we even doing this? Right. So that's your job to kind of keep tracking that. But this is the career kind of education path we've chosen where the classes are like that, where you're just trying to grind through some formulas. You're trying to take a lot of notes and then be able to somehow do this again when you get home, type of thing.
I feel like with calculating all the stuff, it'd be real easy to lose numbers. How do you keep track of them? Like, how do you do it?
You never do it alone, number one, so. Yeah, if any instructor's ever telling you to work alone on your homework, like just leave that class, because that's just wrong. So first of all, you never work alone. If I do work alone, then I'm sending it off to a couple other folks to check it, to go through it, to make sure I haven't missed it. Super easy to do. You miss a square, you miss it to the third, you know? And yeah, you're calculating everything 2 or 3 times to make sure you get the same number each time, but you can make that same mistake over and over. So don't do it alone, would be my answer. None of us do it. Very few. Good. Right, so when you hear me say, okay, well, we want some calculations, I'll go back over this again when that comes closer, but that's the kind of calculation I want. Where you're trying to like best guess, like, is this gonna work or not? What do my numbers say? As far as, is it gonna work? The other thing is, when you think about cross sections, think about tall cross sections, not flat cross sections. So tall cross sections carry load. Good? All right, we're done.
Section of this.
Sure.